Yeah.
Like devil's
Right.
advocate, people who are like, I don't care.
Yeah.
Some don't,
My
some
life.
do, yeah.
Yeah.
Sad but true.
Yeah.
So let's get into this Schramski a little bit. So I'm going to very quickly go through this. The talk is online. I gave it last week, and the YouTube's out there. But I'm just going to. This is all kind of 101 stuff. Thermodynamics, first, second, third law. We covered that. Coal fire, hotter, colder, no effect. Hotter, coal-fired power plants make things hotter. So do nuclear power plants. So do internal combustion engines. So does slash burning. So does incineration, which we kind of talked about a little bit today. So does the greenhouse gas effect. So do thermonuclear weapons. But a refrigerator does not. But it really does. Out the back end of the fridge is coming some heat, and somewhere else there's a coal-fired power plant running the thing. Okay. We've covered all of this, metabolic. Here's some of the biochemistry, the biochemical stuff that we just talked about. And and you can write a whole doctoral thesis on, what's been done here. And it gets pretty complicated and super duper complicated when you look at all of the, thousands of enzymes that are, making our own biological networks function. Okay. I went through the whole 10 megajoules per day, metabolically, 200 technologically, 1200. Here's this 500 exajoules per year. This is what I want to focus on, because I was asked a very challenging question that I was not really able to answer based on what I saw in the Schramski paper. Seen this before. We talked about Iceland a little bit here with very high energy per person. I mean, they are living far from thermodynamic equilibrium, but doing so with relatively little carbon emissions. I mean, they're actually one of the greatest consumers of energy on a per capita basis. So anyway, so here's Schramski 2015. This is one paper that kind of got me started on this whole thing. You've read this, obviously, in 101. So here's Schramski's main figure, showing that humans are basically draining the geochemical, the very ancient biofuels that are buried in the Earth's surface at a phenomenal rate. All of this right here, this 200 or 2,000 zetajoules, so 1 zetajoule is 1,000 exajoules. This is like carbon that's just like sitting like on the beach, for example, in very, very low concentrations, or like at the bottom of the ocean, in the little flakes that fall down there, like stuff that you would have to just mine the entire Earth to actually burn if you were so inclined. So even less accessible than some of these tar sands that we've been talking about. This is the recoverable nuclear energy, and there's also some non-recoverable nuclear energy here too. I mean, the uranium's there, but just the act of like gathering it and concentrating it, you would spend your energy invested on energy return is negative. There's not enough energy to actually pull it out. It would take more than there is to get at it. So what we're really dealing with is this little tiny 40 zetajoule chunk at the top. The 19 zetajoules, that's current potential energy that's just sitting on planet Earth right now, not buried, not stored. And this 2 zetajoules, that's what's being made each year. So you can think of like this 19 or 20 is like kind of what's in your bank account. You got let's just say, $20 in your bank account, $19 in your bank account, and someone's kind of giving you $2 each period, in this case each year. So you got $20 in there, and you're getting an extra 10% of what's already there each year, which is a reasonable investment. I think those okay. I'll take 10% on my investment. The 35 zetajoules, that's kind of what we started with 2,000 years ago. The 23,000, so this is like, after we've, gone through the forests, and this is 1900, so, the Industrial Revolution is in full swing, coal mining's in full swing, all the stuff we covered in 101 and 102 up to this point is going pretty good gangbusters. 100 years ago, we've consumed 4 zetajoules in 100 years, and the question is kind of what's next. What's next? Well, again, 2 zetajoules is the flow. That's what's coming into the planet. Now, I want to look at that briefly, because let's just do that right now. That's what's coming in. If you look, here's what's sort of coming in to planet Earth, being converted from sunlight into biomass. So that's what this is really the rate at which photosynthesis is storing carbon bonds on planet Earth. This is the rate at which humanity is breaking carbon bonds on planet Earth. So we're breaking them at a quarter of the rate at which they're being formed. Right now, that's our 500 exajoules that I just mentioned. Now, here's the math that I wanted to do. So if we look, all bioenergy potential, and I guess before I do it, I want to look at one quick little thing. I want to look at this guy. So here is the so at our rate of consumption 2,000 years ago, we would have had 65,000 years of bioenergy left. This includes the I think it actually includes the recoverable nuclear as well. As it's consumed, the horizon of unsustainability, this sort of omega factor that he mentions, shortens. When the plague happened, it actually sort of flattened out for a while and actually got longer. There weren't people burning down forests and maybe to some extent mining a little bit of coal back then. The plague ends and we again start on our consumption. Zooming in, so this sort of ends at, let's see, 1,000, 1,500. Here's the year 2000 out here. So this little guy right here is a zoom in of this portion of the graph. And you can see by 1970, at our then rate of consumption, we would have had 1,800 years left of this biomass, and that includes coal, oil. I mean, all biomass. But now, in the year 2000, we're down to 1,000 years left. So the problem I want to try to solve, unfortunately, I've only left myself 4 minutes, but we'll try it. I want to show you the conundrum that I ran into the other day when I was trying to look at this problem. So we know that energy, and this is going to be in joules per year, is 500 exajoules, so 500 E18, right? So that's our annual consumption rate. Now what I want to look at in this paper is how much is left, and I'm trying to figure this out. So phytomass stores, now I'm looking at this thing and seeing that there are 20 zetajoules left. Now I'm just going to do a quick and dirty back of the envelope and see, well, how many years are left then? If that's how much left right now, and we're consuming it at 500 exajoules per year, and Schramski, if you listen to this, give me a call because I want to figure out the paper a little bit. I've got 102 students, struggling with this. So 20 zetajoules. Let's put that in. So this is going to be E reserve, let's just call it, and this is just going to be in joules. So we've got joules per year, we've got joules, divide the two, and the number of years should pop out. So I'm just going to put in 20. E, now zeta is e to the 21, because exo is e to the 18. E, 21. And now we're going to call this thing omega, because that's what he calls it in his paper, and this is going to be measured in years. So if we take that number, divide it by that number, well, this came out even differently than I did in the lecture. It comes out to 40. So let's do number. Comes out to 40 years left at our current rate. It's like, okay, I might be alive in 40 years. I might make it to 85. I don't know, but
Good chance.
So what it doesn't assume though, which I kind of took issue with, is
Yeah.
that there's no new production of biomass. Every year plants grow. There's a
Yeah.
deposit like you were talking about.
Yeah, well, that could be where the rub lies, and there could be a little subtlety in there. Is that okay? This new production, maybe it stays constant, because that's basically what the new production is, two zetajoules per year. And if we did this math, so there probably is some like subtleties in there. I'm sure you had a fleet of graduate students running differential equations on these things, and that's where he came out with these longer numbers. And that more than likely, that's exactly where my little error. But if you looked at this graph, you'd say, oh, we're sustainable, because until this left bar gets higher than the right stack, we're still under the quote, photosynthetic ceiling, if you will.
Yeah.
So the question remains, now that we have this knowledge, what do we do with it? So, can we in fact take this, this very pessimistic curve and sort of, start to flatten it out? That's really the question here. And it looks, if you take the second derivative of this curve, it points up. It's positive. It's pointing in the correct sustainable direction. And so maybe that's where it sort of like makes this landing out there several years. So interesting times. Yeah. So anyway, I enjoyed reading. I wouldn't say I took pleasure in reading the paper, but it was intellectually satisfying in terms of kind of telling us where we are currently with our energy reserves. So. Okay, well, I had fun. Hope you all did too, and we'll see you next week. I'll launch the exam. We're actually going to be in.
No,
Thursday.
I won't be here Thursday.
Oh.
Tim Chester and I are going to be in Browning on my NSF grant. So
Well, are we going to be here Thursday? No.
I've asked Mark Olson if he could lecture. If he can, I'll let you know.
Okay.
If not, I think we've covered chapter 4, and that's what the next exam is. So I've prepared you as much as I can. And
Rest is up to
yes,
us.
it's up to you, exactly. Yeah, thanks, Shauna.
I put this chair back.
Okay, thanks.
You can be here tomorrow for the
Yeah,
G92?
I sure will. Yeah, I'll be here tomorrow.